Okay, thanks for checking out Hint. So the plots that you see here are the plots that are requested from part one in project three. And you'll see that you have the air temperature as a function of time in seconds. Actually, I'm missing the units here, so you should always indicate units on both axes. But anyway, you see your data here. Now, one of the things that happens in engineering and science is quite often we'll measure different phenomena in nature or from equipment. We'll get results, temperature, pressure, and so on. And what we'll want to do is to be able to come up with some sort of mathematical formula or equation that we can use to predict how that phenomena is going to, or model how that system is going to behave under different circumstances. In this particular case, we're looking for trying to define some sort of mathematical function that characterizes the shape that you see here for the entire day, and then another one over a range of hours for that day. All right. So the way that we can do this is through a numerical modeling process called curve fitting. And what's really neat about MATLAB is it has a built-in tool in the window, on the pull-down windows rather. If you click on Tools, you can scroll down to Basic Fitting, and a window pops up. And in this window, you have different numerical models that can be used to establish or fit equations onto your data. So let me just click on Show Equation. And then, for example, if I wanted to model this data in a linear fashion, if I click on that, this gives me a linear model or fits a linear trend line to the actual data. And it shows you the equation for that model or that line here. It also shows you that equation over here where you have y is equal to some constant or coefficient p1 times x plus p2. Those values are here. Okay. But obviously, this is not a linear relationship. You can see that there's all kinds of curvature happening in this function, or in this data rather. And so what we really should be thinking about using instead is some sort of polynomial function. So you can see as you start using polynomials, for example, a quadratic, aha, now we're getting some curvature showing up. So we're better able to model the data. However, hopefully it's clear that we need to maybe use a higher order polynomial here. So let's try something really high and look at what happens here. We get an error message saying that this polynomial is badly conditioned, that the x data needs to be scaled and so on. Let me just click OK. Right, so while it does seem to track the data well, we're getting this message that the numerical technique that's used is not functioning very well for this type of data, and that happens sometimes. Now, we got an error message that time that clearly showed us that, but another way that we can actually figure that out, because actually sometimes when you do these um, curve fitting exercises, you may not get that error message using these tools. However, one way to be able to tell is when you look at your coefficients here. Look at the P1 coefficient. It's 10 to the negative 35, all right, e to the minus 35, versus the P9 coefficient is, basically a third. When you have those very large differentials between your coefficients, that indicates or is indicative of numerical instability, and it means we can't, it's not appropriate to use um, these techniques to model the data. All right. So what we'll actually need to do here is, well, one way that we can at least make this work a little bit better for our purposes is to actually more or less scale our data. So what I'll need for you to do is for both of these plots, before you actually use this basic curve fitting tool, you'll need to actually plot these air temperatures as a function of hours. So you need to convert the seconds, convert that into hours, okay? And then plot the air temperature as a function of hours for both of these plots. Then when you apply your curve fitting tools here, whether it's a linear or third or whatever degree polynomial, you should be able to achieve that um, without such a huge differential between um, the magnitudes of your coefficients over here. I would say as long as it's around, um, you know, it's no smaller than maybe 10 to the minus 4 or 5 in your first couple coefficients here, and these might be, you know, um, maybe just a bit less than 1 or around there on the p on your higher order or your higher numbered coefficients, P5, P6, whatever you end up using in terms of your degree for your polynomial. Okay, so again, you'll need to convert your time scale to hours and then apply your function. So once you determine what that function is, you can then, because in part 4 you'll need to compute the error, and so the error there is going to be the difference between what the actual value is and what your numerical model predicts as the value. Okay, so you'll need to take that function that you find, the mathematical formula that you find, and plug in the values, um, and you'll be able to do this in your script very easily. Find out where you have your maximum error, that is the maximum difference between the true value, the measured data value, versus your modeled or predicted data values. Okay, so that concludes the